Hello, my name is Joe Vasta. In this video, we're going to talk about Pascal's tetrahedron. A tetrahedron is a triangular pyramid, a three-dimensional shape composed of four triangular faces. You can actually stack marbles to represent this. There are 120 marbles in this picture. 120 is a tetrahedral number. We'll talk about that later. You might want to pause the video and download these handouts. That way you can fill out the handouts as you watch this video. Before we get to Pascal's tetrahedron, let's talk about Pascal's triangle. Pascal's triangle was discovered hundreds of years before Pascal was born. Nevertheless, we'll still call it Pascal's triangle. We'll use an equilateral triangle and we'll label the little white triangles. The top white triangle gets a 1. In fact, the next two triangles get 1s as well. We'll put 1s down the left and right sides of Pascal's triangle. How do you find the internal triangles? You add the two entries right above each triangle. Look at the red dot. For this triangle, we will add 1 plus 1, and we end up getting 2. You might want to pause the video to see if you can fill out the rest of this diagram. 1 plus 2 equals 3. 2 plus 1 equals 3. 1 plus 3 equals 4, 3 plus 3 equals 6, 3 plus 1 equals 4. Next row, 1 plus 4 equals 5, 4 plus 6 equals 10, 6 plus 4 equals 10, 4 plus 1 equals 5. Next row, 6, 15, 20, 15, 6. The next row, 7, 21, 35, we notice something. Whatever's on the left side is mirrored over to the right side. This is called symmetry. We could just fill out the rest of this row by copying what's on the left side. Notice that in the middle, this row we have two 35s. I call that a plateau. Next row, 8, 28, 56, 70. Now I'm right in the middle, so I'm going to use symmetry to fill out the right side of that row. Notice 70 is in the middle. I'll call that a peak instead of a plateau. Pascal's triangle contains peaks and plateaus. We can continue writing down rows in Pascal's triangle. It never ends. It just keeps going down row after row. Let's get rid of the arrows. The rows of Pascal's triangle have numbers associated with them. We start counting at 0, so the first row is row 0. The second row is row 1. The advantage to this labeling is that the row number of each row is exactly the second entry of that row. For example, row 8 has an 8 in the second entry. Row 50 has 50 in its second entry. Now each row has numbers. We'll call them entries. Let's look at row 8. The first entry is entry 0, and we go all the way through entry 8. We see Pascal's triangle has line symmetry. Whatever you see on the left, you see on the right. Let's take a look at the sum of each row. Look at row 3. Add up those numbers. 1 plus 3 plus 3 plus 1 equals 8. We'll do this with all these rows. You might notice that those numbers on the right, 1, 2, 4, 8, etc., are powers of 2. For example, the sum of row 8 is 2 to the 8th power. The sum of row 50 is 2 to the 50th power. Let's take a look at the diagonals. Natural numbers, 1, 2, 3, 4, 5, 6, etc. Triangular numbers. A number that can make a triangular marble pattern is a triangular number. The first one being 1, and then 3, 6, 10, 15, 21, etc. These triangle figures are two-dimensional. Tetrahedral numbers. A number that can make a tetrahedron marble pattern is a tetrahedral number. 1, 4. Look at the diagram on the right. You put 3 marbles down and you stack another marble on top of that. It looks like a little tetrahedron or a little pyramid. These figures are three-dimensional. Look at the diagram on the bottom. Those are pyramids from the top view. We're looking down. Let's continue. 10, 20, 35, 56, etc. At the beginning of this presentation, we saw a pyramid of 120 marbles. 120 is a tetrahedral number. Pentatope numbers. The pentatope numbers are 1, 5, 15, 35, 70, etc. These numbers describe hypertetrahedrons or four-dimensional tetrahedrons. We're going to left justify Pascal's triangle. We're going to take a look at the sum of the diagonals. Our first diagonal just has a 1. Our second diagonal also has just a 1. When we get to the third diagonal, we have 1 plus 1, which equals 2. 1 plus 2 equals 3. 1 plus 3 plus 1 equals 5. 1 plus 4 plus 3 equals 8. We continue with the sums. Look at those sums. They happen to be the Fibonacci numbers. Binomial coefficients. Let's evaluate x plus y to the 4th power. X plus y is called a binomial because it has 2 terms. In an algebra class, they might tell you to do this. You do a whole bunch of algebra and you get your answer. This is probably why a lot of people drop their math class, because wouldn't you rather be spending time at the beach? Let's find another way of doing this problem. Let's use Pascal's triangle to figure out x plus y to the 4th power. Take a look at the 4. That power tells us to go to row 4. 1, 4, 6, 4, 1. Those happen to be the coefficients of our answer. You might also notice, reading from left to right, that we have an x to the 4th, x to the 3rd, x to the 2nd, x to the 1st, and x to the 0 power. X to the 0 is 1. That's why you don't see it. Also, reading from left to right, we have a y to the 0 power, which you don't see, y to the 1st, y to the 2nd, y to the 3rd, y to the 4th. This process of raising a binomial to a power is called the binomial theorem. If you wanted to compute x plus y to the 50th power, then you can find those coefficients in row 50. Pascal's triangle is a triangular array of binomial coefficients. Let's take a look at a famous coin problem. Flip a coin 6 times. How many different ways can the outcome have 4 heads and 2 tails? Well, we could list out all the possibilities. Head, 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 tail, tail, or head, 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 tail, etc. This is not fun because the list is going to be kind of long. It would ruin your day. Another way of doing this problem, look at the 6. That's how many times you're flipping the coin. Notice that 6 is 4 plus 2. So go to row 6 of Pascal's triangle. I'm in row 6. Look at the 4 and the 2 circled in green. Select one of those numbers, either the 4 or the 2. I'm going to go ahead and select the 4. That tells me to go to entry 4 in row 6. Now remember, the first entry in row 6 is entry 0, so we'll just count over. Put your finger on entry 0 and count over 4. And we get 15 for our answer. Let's do this a little bit differently. We're in row 6. Now let's select the 2 instead of the 4. That tells me to go to entry 2 in row 6, count over 2 spots, and our answer is still 15. The symmetry of Pascal's triangle is really seen here. And also, if we flip the coin 50 times, we would go to row 50. Let's consider some more counting problems. Here's our coin problem, but here's a new problem. How many different words can be formed using all the letters of the word boo-boo? Let's list them out. Now, a word is a concatenation of letters, so O-O-O-O-B-B is considered a word. We could also say O-O-O-B-O-B, etc. We can see that this is pretty much the same as the coin problem. You get the same answer. Here's another counting problem. A family has 6 kids. A group of 4 is to rake leaves, and a group of 2 is to wash the car. How many ways can the groups be formed? Let me introduce you to the 6 kids. The oldest one is the tallest one. We can assign the chores like this: leaf, 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 car, car. So the 2 little ones are washing the car. Or we can assign the chores like this: leaf, 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 car, leaf, car, etc. You can see that this is the same as the coin problem. You get 15. Pascal's triangle can solve all these problems. Can we do the coin problem without listing all the possibilities and without using Pascal's triangle? The answer is yes. We'll use something called combinations. We'll say 6 choose 4, flip a coin 6 times, we want exactly 4 heads. Here are some notations with the letter C. Here's the more famous notation with the big parentheses. Now, what is the formula for combinations? We are going to create a fraction. Put 6 on the top and 4 on the bottom. Another number goes on the bottom, and that would be 6 minus 4, which is 2. 2 also goes on the bottom. But you're not just going to put those numbers in the fraction. You're going to put little exclamation marks near each number. Those mean factorial. 6 factorial, which is on the top, means 6, 5, 4, 3, 2, 1, all multiplied. Let's expand that out. I'm going to cancel some of these numbers and get 30 over 2, which gives me 15. Notice that Pascal's triangle is a triangular array of combinations. Let's get back to Pascal's triangle. We'll get rid of the black triangles. Let's stretch it horizontally and compress it a little vertically. Let's rotate it. The entries of Pascal's triangle lie on a square grid. We'll see a connection to this fact later on. We are done with Pascal's triangle. Let's take a look at Pascal's tetrahedron. Let's use this stack of wooden marbles to investigate Pascal's tetrahedron. First of all, we are looking at a regular tetrahedron. That's where all the faces are equilateral triangles. Sometimes it's called a regular triangular pyramid. Let's start with the top marble. You probably guessed that it gets labeled with a 1. Let's focus on the next level. For each marble we ask, how many marbles are touching it from the level above? Then we add those marbles. Each marble on the second level has only one marble from above touching it, so they each get labeled with a 1. In fact, the marbles down the edges each get labeled with a 1 for the same reasoning. Let's take a look at this marble that the red dot is near. How many marbles are touching it from the level above? 2 marbles, a 1 and a 1. So 1 plus 1 is 2. Now let's take a look at this marble right here. How many marbles are touching it from the level above? 2 marbles, a 1 marble and a 2 marble. 1 plus 2 equals 3. Over here, we do the same thing. 2 plus 1 equals 3. We do the same thing on this side of Pascal's tetrahedron, where the red dot is. We end up getting 2, 3, and 3. In fact, if you walk around this pyramid, and you'll see 3 more marbles that we could label 2, 3, 3. Now, there's a marble on the inside, bottom level, that we cannot see even if we walked around this pyramid. I'll call it the hidden marble. It has 3 marbles from the level above touching it, so those marbles are 2, 2, and 2. We add those together, and that hidden marble gets labeled 6. Notice that Pascal's triangle is seen on each side of Pascal's tetrahedron. It's difficult to use this marble diagram to label the next level down. So we'll take a look at dots and line segments. Let's label Pascal's tetrahedron. We're going to start by putting a 1 on the top dot. For each dot, we ask, how many dots are connected to it from the level above? For each dot on the edges, there is just 1 dot connecting from above. Those dots get labeled with a 1. The red level is complete. The blue level is complete. Let's work on the orange level. Look at this little red marker right here. That orange dot has 2 black line segments going up to the blue level. Add those 2 numbers from the blue level. 1 plus 1 equals 2. The orange dot over here also has 2 line segments going up to the blue level. Add those 2 blue ones. 1 plus 1 equals 2. This orange dot back here, on the back part of this, has 2 line segments going up to the blue level. So we have 1 plus 1 equals 2. This green dot here has 2 line segments going up to the orange level. We have 1 plus 2 equals 3. Green dot right here, 2 plus 1 equals 3. In fact, along the perimeter of this green level, we can label the rest of those dots with 3s. Now, this middle dot right here, this is the only dot in the picture that has 3 line segments going up to the orange level. Look at those numbers on the orange level. It's kind of hard to see. 2 plus 2 plus 2 equals 6. That was the hidden marble. This method is also a complicated way of labeling Pascal's tetrahedron. We need an easier way. Let's get rid of the numbers. Let's move this pyramid to the left. Let's look at a property. On the right, we have a cube grid. The entries of Pascal's tetrahedron lie on that cube grid, just like the entries of Pascal's triangle lie on a square grid. The red level is there, the blue level is there, orange level, green level. This means that you can create a physical model of Pascal's tetrahedron. Now let's get back to Pascal's tetrahedron. We are going to remove most of the black edges connecting the levels. Since we want to label the vertices without getting confused, let's represent Pascal's tetrahedron a little differently. We'll get rid of the figure on the left. Now I'm going to tweak the diagram a little. This is just a matter of style. And we see that there are levels to Pascal's tetrahedron. The level numbers start at 0, just like row numbers and entry numbers on Pascal's triangle. So we see level 0, level 1, level 2, level 3, etc. We're going to get rid of the figure on the right. You can think of Pascal's tetrahedron as a growing triangle. We'll start labeling this. Red level 0 gets a 1. We'll use level 0 to label level 1. We put 3 blue dots on level 0 at the corners. These 3 blue dots form a triangle that corresponds to blue level 1. We'll do this labeling 1 dot at a time. The blue dot at the top of level 0 is touching 1 number. That is the red 1. So the corresponding triangle on level 1 just gets a 1. Red level, we put a dot on the bottom left corner. This blue dot is touching just 1 number, blue level, we put a 1. Red level, we put a dot on the bottom right corner, touching 1 number, blue level, we put a 1. Now we're ready to label level 2. We put 6 orange dots on level 1. These orange dots correspond to the orange level 2. We'll do this labeling 1 dot at a time. The orange dot at the top of level 1 is touching 1 number. That is the blue 1. So the corresponding triangle on level 2 just gets a 1. Blue level, our dot is touching 2 numbers, 2 blue triangles, So we add those numbers. 1 plus 1 equals 2. Orange level, we put a 2. Blue level, 1 plus 1 equals 2. Orange level, 2. Blue level, the dot touches one number, a blue 1. Orange level, 1. Blue level, the dot is touching two numbers, 1 plus 1. Orange level, 2. Blue level, the dot is touching one number, 1. Orange level, 1. Now we're ready to label level 3. We put 10 green dots on level 2. These 10 green dots correspond to green level 3. We'll do this labeling one dot at a time. You might want to pause the video to see if you can fill out the rest of the diagram. Also, if you are watching this video, feel free to skip ahead due to sheer boredom. Orange level, 1. Green level, 1. Orange, 1 plus 2. Green, 3. Orange, 1 plus 2. Green, 3. Orange, 2 plus 1. Green, 3. Orange, 2 plus 2 plus 2. This is the first time the dot is touching three numbers. Green, 6. This was the hidden marble. Orange, 2 plus 1. Green, 3. Orange, 1. Green, 1. Orange, 1 plus 2. Green, 3. Orange, 2 plus 1. Green, 3. Orange, 1. Green, 1. Now there's level 0 through level 3 of Pascal's tetrahedron. Notice if you rotate Pascal's tetrahedron 120 degrees, you get the same numbers. This is called rotational symmetry by 120 degrees, which is a very neat property. Remember, Pascal's triangle has line symmetry, and this guy here, the tetrahedron, has rotational symmetry. Here's the old diagram we labeled using dots and line segments. If we continue to label the figure on the right, it would get pretty confusing because we are trying to do this in 2 dimensions. We'll continue with the figure on the left. Let's get rid of the figure on the right. Let's do level 4. Feel free to pause the video and fill out the next 2 levels on your own. Green level. I put 3 yellow dots in the corners. Each yellow dot is touching just one number, a green 1. Yellow level. Put the 3 ones in the corners. Green, 1 plus 3. Yellow, 4. Green, 1 plus 3. Yellow, 4. Green, 3 plus 3. Yellow, 6. Green, 3 plus 3 plus 6. Yellow, 12. Green, 3 plus 3. Yellow, 6. Green, 3 plus 1. Yellow, 4. Green, 3 plus 6 plus 3. Yellow, 12. Green, 6 plus 3 plus 3. Yellow, 12. Green, 3 plus 1. Yellow, 4. Green, 1 plus 3. Yellow, 4. Green, 3 plus 3. Yellow, 6. Green, 3 plus 1. Yellow, 4. Woo! We just completed level 4. Let's do level 5. Yellow level, I put 3 purple dots in the corners. Each purple dot is touching just one number, a yellow 1. Purple level, put the 3 ones in the corners. Yellow, 1 plus 4. Purple, 5. Yellow, 1 plus 4. Purple, 5. Yellow, 4 plus 6. Purple, 10. Yellow, 4 plus 4 plus 12. Purple, 20. Yellow, 4 plus 6. Purple, 10. Now we'll use the rotational symmetry to get more numbers on level 5. Purple rotates 120 degrees clockwise. That gives us 5 more numbers for free. Purple rotates 120 degrees clockwise, 5 more numbers. Looking back up at the yellow, 6 plus 12 plus 12, purple, 30. Purple, rotate and fill the other 2 triangles with 30s. Let's get rid of all the dots. Beautiful. Maybe you want to pause the video and try level 6 on your own. There's level 6. Let's take a look at something very interesting. Here's Pascal's triangle up to row 4. Look at the entries of row 4. We write them alongside the triangle. Now multiply each row by the number that's next to it, and look what it gives us. Pascal's tetrahedron, level 4. Here's Pascal's triangle up to row 5, multiply by row 5, and get Pascal's tetrahedron, level 5. This is another way of generating Pascal's tetrahedron. Let's take a look at the sum of each level. Look at the orange level, level 2. Add up those numbers. 1 plus 2 plus 2 plus 1 plus 2 plus 1 equals 9. We'll do this with all the levels. You might notice that those numbers, 1, 3, 9, 27, etc., are powers of 3. For example, the sum of level 5 is 3 to the 5th power. The sum of level 50 is 3 to the 50th power. We saw something similar with Pascal's triangle, and the sum of each row being a power of 2. Trinomial coefficients. Let's evaluate x plus y plus z to the 4th power. X plus y plus z is called a trinomial because it has 3 terms. Let's use Pascal's tetrahedron to figure out x plus y plus z to the 4th power. Take a look at the 4. That power tells us to go to level 4. Those 15 numbers happen to be the coefficients of our answer. Let's see how the variables are computed. We have the variables x, y, and z on the corners of this level or this triangle. Look at the top triangle right there. That top triangle is going to have an x to the 4th. Each time you drop down a row, the exponent drops by 1 number. So we'll have x to the 4th, x cubed, x squared, x, and x to the 0 on the bottom row. Remember, x to the 0 is 1. We're going to do the same thing with y. Look at the triangle near y. That's going to be y to the 4th. Each time you travel to the next diagonal, here's the next diagonal here, the exponent drops by 1 number. So we have y to the fourth, y cubed, y squared, y to the 0. We'll do a similar thing with z, starting off with z to the fourth, z cubed, z squared, z, and z to the 0 power. There's the answer. If you wanted to compute x plus y plus z to the 50th power, then you can find those coefficients in level 50. The three-dimensional Pascal's tetrahedron is loaded with trinomial coefficients, just like the two-dimensional Pascal's triangle is loaded with binomial coefficients. A two-dimensional Pascal's triangle dealt with a coin, or a two-sided die. A three-dimensional Pascal's tetrahedron deals with a three-sided die. Well, here's the problem, and it includes a three-sided die. But what does a three-sided die look like? Well, you can think of it as an equilateral triangular prism. We see side A and side B in the figure, and side C is on the bottom. Now, technically, this figure has 5 sides, but if it's long enough, it will never land on those triangles. If you don't like the three-sided die, then you can use this spinner. A three-sided die is labeled A, B, and C. Roll this die 6 times. How many ways can the outcome have 3 A's, 2 B's, 1 C? Well, we could list out the possibilities. A, B, B, C. Or A, B, C, A, B, etc. Well, this is not fun. So let's use the tetrahedron. Look at the 6. That's how many times you're rolling the die. Notice that 6 is 3 plus 2 plus 1. So go to level 6 of Pascal's tetrahedron. Look at the 3, 2, 1 that's circled in green. Select 2 of those numbers. I'm going to select the 3 and the 2. 3 plus 2 equals 5. That tells me to go to row 5. Look at the 3 and 2 circled in brown. Select one of those numbers. I'm going to go ahead and select the 3. That tells me to go to entry 3. We count over and we get 60. Let's do this a little bit differently. Roll the die 6 times. We're in level 6. Look at the 3, 2, 1 circled in green. Select 2 of those numbers. This time I'm going to select the 2 and the 1. 2 plus 1 equals 3. That tells me to go to row 3. Look at the 2 and 1 circled in purple. Select one of those numbers. I'm going to select the 2. That tells me to go to entry 2. We count over and get 60 for our answer. There's actually 6 different ways to land on 60. You'll end up landing on this ring of 60s. If we rolled that three-sided die 50 times, we would go to level 50. Let's consider some more counting problems. Here's our three-sided die problem, and here's a new problem. How many different words can be formed using all the letters of the word banana? Let's list them out. A, N, N, B, A, N, B, A, N, etc. We can see that this is pretty much the same as the three-sided die problem. You will get the same answer, 60. Here's another counting problem. A family has 6 kids. A group of 3 is to rake leaves. A group of 2 is to wash the car. And 1 is to pick up dog poop. How many ways can the groups be formed? There are the 6 kids. we can assign chores like this. Leaf, 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 car, car, poop. So the little guy is picking up the dog poop. Or we can assign them like this. Leaf, car, poop, leaf, leaf, car, etc. We can see that this is the same as the three-sided die problem. You get 60. Pascal's tetrahedron can solve all these problems. How can we solve this problem without listing all the possibilities and without Pascal's tetrahedron? We'll use something called permutations with repeated elements, or a hybrid combination permutation. We will say 6 choose 3 choose 2 choose 1. There's the C notation, and there's the big parentheses notation. You can put 6 factorial on the top and 3 factorial, 2 factorial, 1 factorial on the bottom of the fraction. Let's expand that out. We cancel, and our answer is 60. Notice Pascal's tetrahedron is loaded with these hybrid combination permutations. We'll put Pascal's triangle and Pascal's tetrahedron side by side. We'll also throw the numbers in there. This is beautiful. If a friend or a family member is trying to get political with you, then why don't you just show them Pascal's triangle and Pascal's tetrahedron side by side? What do you have to lose? Maybe you can carry a picture of this in your wallet or on your cell phone in case of emergencies. Now, can this concept be extended to higher dimensions? Let's take a look at Pascal's tetrahedron. Notice that Pascal's tetrahedron is really a growing triangle. Pascal's hypertetrahedron is the triangle, but in 4 dimensions. So Pascal's hypertetrahedron is a growing tetrahedron. To avoid confusion, we'll call the levels ranks. It's still an object in the 4th dimension that we humans cannot fully comprehend, but if we think of it as a growing tetrahedron, then we could label it. Pascal's hypertetrahedron is also called Pascal's pentope. Let's label Pascal's hypertetrahedron. Well, rank 0 has 1 level, the red triangle, and we label it 1. In fact, the top red level of each rank gets a 1. We're going to fill out the blue level of rank 1. To do that, we'll put 3 dots on the corners of rank 0. Each blue dot is touching just one number, that red 1. So put 3 1s in the blue level of rank 1. This was how we filled out Pascal's tetrahedron. Now things are going to be different when we fill out the blue level of rank 2. The pattern has been to add numbers from the previous row for Pascal's triangle, previous level for Pascal's tetrahedron, and now the previous rank for Pascal's hypertetrahedron. Numbers from the red and blue levels of rank 1 will be added to get numbers for the blue level of rank 2. Look at rank 1. Put a blue dot on the red level and a circle on the blue level. Both of those correspond to the top position of the blue level from rank 2. 1 plus 1 equals 2. So put a 2 on the top of the blue level for rank 2. Rank 1. Red 1 plus blue 1 equals rank 2, 2. Rank 1. Red 1 plus blue 1 equals rank 2, 2. Rank 1. Put 6 orange dots on the blue level. We compute the last level of rank 2 by doing what we did with Pascal's tetrahedron. This will always be the case when computing the last level of each rank. Rank 2 is complete. Suppose you want to annoy your roommate, then just turn up the volume and let this video play. Let's fill out rank 3. Rank 2. Red 1 plus blue 2 equals rank 3, 3. Rank 2. Red 1 plus blue 2 equals rank 3, 3. Rank 2. Red 1 plus blue 2 equals rank 3, 3. Rank 2. Blue 2 plus orange 1 equals rank 3, 3. Rank 2. Blue 2 plus blue 2 plus orange 2 equals rank 3, 6. Rank 2. Blue 2 plus blue 2 plus orange 2 equals rank 3, 6. Rank 2. Blue 2 plus orange 1 equals rank 3, 3. Rank 2. Blue 2 plus blue 2 plus orange 2 equals rank 3, 6. Rank 2. Blue 2 plus orange 1 equals rank 3, 3. Rank 2. Put 10 green dots on the orange level. We compute the last level of rank 3 by doing what we did with Pascal's tetrahedron. Rank 3 is complete. Let's take away the dots. That looks great. Pascal's hypertetrahedron has major symmetry. Also, Pascal's tetrahedron is seen on the last level of the ranks. Let's take a look at the sum of each rank. Look at rank 2. Add up those numbers. 1 plus 2 plus 2 plus 2 plus 1 plus 2 plus 2 plus 1 plus 2 plus 1 equals 16. We'll do this with all these ranks. You might notice that those numbers, 1, 4, 16, 64, etc., are powers of 4. For example, the sum of rank 3 is 4 to the third power. The sum of rank 50 is 4 to the 50th power. Two-dimensional Pascal's triangle, powers of 2. Three-dimensional Pascal's triangle, which was Pascal's tetrahedron, powers of 3. Four-dimensional Pascal's triangle, powers of 4. 10-dimensional Pascal's triangle, powers of 10. Let's do rank 4. Feel free to pause the video and fill it out yourself. Rank 4, top level, which is red, gets a 1. Rank 3. Red 1 plus blue 3 equals rank 4, 4. Rank 3. Red 1 plus blue 3 equals rank 4, 4. Rank 3. Red 1 plus blue 3 equals rank 4, 4. Rank 3. Blue 3 plus orange 3 equals rank 4, 6. Rank 3. Blue 3 plus blue 3 plus orange 6 equals rank 4, 12. Rank 3. Blue 3 plus blue 3 plus orange 6 equals rank 4, 12. Rank 3. Blue 3 plus orange 3 equals rank 4, 6. Rank 3. Blue 3 plus blue 3 plus orange 6 equals rank 4, 12. Rank 3. Blue 3 plus orange 3 equals rank 4, 6. Rank 3. Orange 3 plus green 1 equals rank 4, 4. Rank 3. Orange 3 plus orange 6 plus green 3 equals rank 4, 12.
Rank 3. Orange 3 plus orange 6 plus green 3. Rank 4, 12. Rank 3. Orange 6 plus orange 3 plus green 3. Rank 4, 12. Rank 3. Orange 6 plus orange 6 plus orange 6 plus green 6. Rank 4, 24. This is the first time we had to add 4 numbers. Most entries in Pascal's hypertetrahedron are gotten by adding 4 numbers.
Rank 3. Orange 6 plus orange 3 plus green 3, rank 4, 12. Rank 3. Orange 3 plus green 1, rank 4, 4. Rank 3. Orange 3 plus orange 6 plus green 3, rank 4, 12. Rank 3. Orange 6 plus orange 3 plus green 3 equals rank 4, 12. Rank 3. Orange 3 plus green 1, rank 4, 4. Rank 3, put 15 yellow dots on the green level. We compute the last level of rank 4 by doing what we did with Pascal's tetrahedron. Rank 4 is complete. Let's take away those dots. Nice picture. The sum of rank 4 is 256, or 4 to the 4th power. Now let's look at something neat. Here's Pascal's tetrahedron up to level 4. We write row 4 of Pascal's triangle alongside this tetrahedron. Now multiply each level by the number that's next to it, and look what it gives us. Pascal's hypertetrahedron, rank 4. Just like Pascal's triangle lies on a square grid and Pascal's tetrahedron lies on a cube grid, Pascal's hypertetrahedron lies on a hypercube grid. On the right, we have a representation of a hypercube, or a 4-cube, or a tesseract. It has many names. We humans cannot fully comprehend this hypercube, and this is just a cheap representation. You might be able to see 8 cubes in this hypercube, but that is a topic for another presentation. We put rank 0 in the corner. Rank 1 goes there. I'll need to extend this hypercube out a little to get part of the grid for rank 2. There's rank 2. This is absolutely amazing. A 2-dimensional Pascal's triangle was used for a 2-sided die. A 3-dimensional Pascal's triangle is used for a 3-sided die. A 4-dimensional Pascal's triangle is used for a 4-sided die. In fact, a 6-dimensional Pascal's triangle would be used for a 6-sided die. Well, instead of a 4-sided die, I'm going to look at the nonsense problem. How many different words can be formed using all the letters of the word nonsense? This is like the banana problem. Let's list out the possibilities. N-N-N-E-E-S-S-O, N-N-E-N-E-S-O-S, etc. That's not fun. Let's use permutations with repeated elements or hybrid combination permutations. I'll show you the formula first, and then Pascal's hypertetrahedron after. We have 8, choose 3, choose 2, choose 2, choose 1. There's the C notation. There's the big parentheses notation. You put 8 factorial on the top of the fraction and 3 factorial, 2 factorial, 2 factorial, 1 factorial in the denominator. Let's expand that out. We'll cancel. And we end up getting 1,680. Let's do this problem using Pascal's hypertetrahedron. Look at the 8. That's how many letters the word nonsense has. Notice that 8 is 3 plus 2 plus 2 plus 1. So go to rank 8 of Pascal's hypertetrahedron. There's rank 8. Let's fill in the numbers. Now look at the 3, 2, 2, 1 circled in brown. Select 3 of those numbers. I'm going to select the 3, 2, and 2. 3 plus 2 plus 2 is 7. That tells me to go to level 7. Look at the 3, 2, and 2 circled in red. Select 2 of those numbers. I'm going to select 3 and 2. 3 plus 2 equals 5. That tells me to go to row 5. Now look at the 3 and 2 circled in green. Select one of those numbers. I'm going to select the 3. That tells me to go to entry 3. We count over and we get 1,680 for our answer. Pascal's hypertetrahedron did it for us. So take a look at this. We have 12 different ways we could have done this problem. There's 12 ways to land on 1,680. I've grouped them in gray. Let's get rid of this problem. We are going to now look at quadrinomial coefficients. Let's evaluate x plus y plus z plus w to the 8th power. X plus y plus z plus w is called a quadrinomial because it has 4 terms. 2-dimensional Pascal triangle binomials. 3-dimensional Pascal's triangle trinomials. 4-dimensional Pascal's triangle quadrinomials. Let's use Pascal's hypertetrahedron, the 4-dimensional Pascal's triangle, to figure out x plus y plus z plus w to the 8th power. Now the power tells us to go to rank 8. Those 165 numbers that you see on the screen happen to be the coefficients of our answer. So the answer is fading in. Let's get rid of the triangles. If your math teacher makes you do a problem like this, then it's time to drop the class. Let's look at this polynomial one level at a time. Level 0, level 1, level 2, level 3, level 4, level 5, level 6, level 7, and level 8. Let's be a little artistic and express rank 8 of Pascal's hypertetrahedron differently. Excellent. The sum of rank 8 is 65,536, or 4 to the 8th power. I actually added all of those numbers, all 165 of those numbers, to check that. Well, we're done here. Hope you enjoyed this presentation. If you're on a date and you experience awkward silence, then why don't you bring up Pascal's hypertetrahedron? What do you have to lose? Have a great day.